Tonight we're going to add in angles to circular motion. So imagine if you take something traveling in a circle and you tilt the whole circle slightly. We're going to learn about what happens when you do that. The most common and most useful application of what we're going to do tonight is keeping cars on the road when it's snowy or icy. So I used to live in Illinois where it snows a lot. And if you're driving in the snow, there's not much friction between your tires and the road. And so if you make a turn, there's no friction to provide a centripetal force or very little friction to provide a centripetal force toward the center of the turn. And so your car might not make the turn. You might just keep going straight and fly off the road. So in places like Illinois where it snows a lot and there's a chance there won't be any or very little friction to keep the car on the road, what they do is they bank or incline the road a little bit. So the road is made so that there's a slight angle. And then the normal force, part of it gets directed toward the center of the circle because the road is banked. And so you don't actually need friction to keep the car on the road anymore. The normal force, the x component of that normal force, is what ends up keeping the car on the road. So kind of a summary of that. Friction is usually the centripetal force for turning cars, but if the turn is banked or angled up a little bit, then friction isn't required. And if you haven't got what I mean by bank, so imagine that a flat circle on a road, and instead we angle that up a little bit, so you kind of go up and around instead of just around. And like I said, when that happens, your normal force then has a component toward the center and a component balancing gravity. And in this case, if the angle of the bank is theta, then the angle between the y-axis and the normal force is also theta. So the x component would actually be normal times sine theta, and the y component would actually be normal times cosine theta, because the y would be adjacent and the x would be opposite. Now let's look at some applications of this. First question. If a turn is banked at the proper angle, a car can round a corner without any assistance from friction between the tires and the road. So this is like what we had to do with roads in Illinois. Find the appropriate banking angle for a 900 kilogram car traveling at 20.5 meters per second in a turn of radius 80.5 meters. So if a car is going around a circle, there's going to be some forces on it. First, this is on Earth, so our car is going to have gravity pulling it down. And then if our car goes in a circle, we can basically imagine that car coming at us. So here are my car's headlights. This is going to be a terrible, terrible car. So I guess that's my car. So the car's coming at us. The normal force on that car is now at an angle. And with respect to the y-axis, that angle's theta, if we call this angle theta. So our car is kind of on a ramp. And you might remember from forces on ramps that the normal force is therefore angled. That means that there's going to be a x component of the normal force and a y component of the normal force. So we take that normal force, so I'll draw this a little clearer, and we can split it into its y components, and we can split it into its x components, normal x. Now the car is not going to fly up or fall down, so a couple things I noticed right away is that the normal y force is going to equal gravity. Okay, and we can go ahead and rewrite that and say n cosine theta equals mg, so I notice that's going to be true. And then the nx force is going to be our net force, because the normal cosine equaling gravity means up and down add to 0. That's the only way these could be equal, is if we subtracted them and they were 0. So up equals down, and then we have a net force that is the x component of the normal force. So that's our net force. And we can also rewrite this to say that n sine theta equals the centripetal force, or m v squared over r. And so I got that out of dividing the normal force into its x component, which here would be n sine theta, because the way I drew my diagram, the angle here has the y part adjacent and the x part opposite. So my n sine theta is equal to my net force and my centripetal force. And I'm looking for this angle theta. To get theta, I'm going to have to know everything else in the equation, so let's see what I know. The car has a mass of 900 kilograms, so I know the mass. Speed of 20.5 meters per second, I know the velocity. Radius of 20.5 meters, I know the radius. But I don't know the normal force, so this I don't know. I do have two equations though, so what if I solved this equation for n? So come down here. N cos theta equals mg. So now I need to solve for n, so n equals mg over cos theta. And I can plug that in for n here. So let's do that. Got mg over cos theta times sine theta equals mv squared over r. Now notice here that I could rewrite this side to have mg times sine over cosine theta equals mv squared over r. I'm going to make clean up this slide, and we're going to keep this line that we just got to here, mg sine theta over cosine theta. Before we do that, I do want to review real quick. So notice some steps I did. First, I drew a free body diagram that helped me out. Then I wrote some equations for x and y. I noticed that the x and y components had to be equal because up would equal down. The car doesn't fly up or fall down. So n cosine theta had to equal mg. And then I knew that n sine theta was my centripetal force, and I just set it equal to the equation for centripetal force. Then I started solving. So the physics was the free body diagram. Up equals down because it's not flying up or falling down. So as far as y is concerned, the situation's in equilibrium. And then saying, well, n sine theta then has to be my centripetal force because the up and down forces will cancel, leaving me with just n sine theta as my net force. And in a circle, the net force is the centripetal force. This is where we got to on the last slide. And remember, I'm solving for theta. The reason I rearranged sine over cosine is because I realized that that was going to be tangent. So mg tan theta equals mv squared over r. That helps me out because now I only have one theta to worry about. These are all, both sides are just multiplied, so the m's can cancel real fast. We get rid of that. We've got g tan theta equals v squared over r. So tan theta equals v squared over rg. And therefore, ending this out, theta is the inverse tangent of v squared over rg. We can fill in all our numbers now. Theta equals inverse tangent 20.5 meters per second, and that gets squared, over the radius 35 meters times gravity on Earth 10 newtons per kilogram. And now we see what we get. Just realized I made a mistake. On my iPad it's hard to see the edges of the screen. This isn't 35 meters, it's 85 meters. So when I do this math out, inverse tangent and then all of that, on my calculator I got theta is 26.3 degrees, which I imagine the first time I did this I just rounded somewhere along the way, don't remember where, but that is my angle. So that's how we would bank the turn. And notice the masses ended up not mattering. So no matter the mass of the car, if we know they're going to go around the turn at that speed, that should be our angle. So there's one use, and this is exactly how they design roads in Illinois, where I was born, because it snows and you can't depend on friction to keep your car on the road. So there we go. That was a lot. I encourage you especially to go watch the first part of this again, where I explain, like, okay, I did the free body diagram, then I set up how my forces would work out. And then the only real new thing here is whenever you find the net force, setting it equal to m v squared over r. So that's really the only new thing in this unit, is doing that part. All right, another example, maybe less everyday real life, more fun real life. So a swing ride at a carnival consists of chairs that are swung in a circle by 15mm cables attached to a vertical rotating pole. So have you ever seen the ride that has people sit in swings and then it starts to turn and they fly up in the air? That's what this is. If the mass of the chair and the rider is 179 kilograms, A, determine the tension in the cable, B, find the speed of the chair. I'm going to try to go through this quick and simple. Let me point out that A is actually not going to require me to know anything about circles. We're going to do it real fast without circles, and then B is the one where I've actually got to know about circles. So let's look at that. I'm going to save space by drawing forces right on this. So first, my proper free body diagram I'm going to do in purple. This box will have gravity acting on it, and it will have tension acting on it. And by the way, if you were drawing a free body diagram, that's all you would draw, is just the tension and the gravity. You don't want to do components on your proper free body diagram because those are not real forces. So when we break this into, oh, well, there's a tension Y and there's a tension X, that actually shouldn't be drawn on your free body diagram. Since this is 60 degrees, this angle would also be 60 degrees. We basically form two identical triangles here. So this is 60 degrees. And sorry, Edgar, I'm not going to take the time to convince you. We could do that after class if you want to. So that's 60 degrees there, meaning that Ty is just T cosine 60, and Tx is T sine 60. Because here the x part would be opposite and the y part would be adjacent. I can also see pretty clearly that there's no acceleration up or down in x or y, so my up and down forces are equal, meaning that Ty, or T cosine 60, is equal to my force of gravity, or mg. And so I can actually right now just find the tension for part A by dividing by cosine 60. So T equals mg over cosine 60 degrees. And I could plug that in real fast. T equals 179 kilograms times 10 newtons per kilogram divided by the cosine of 60 degrees. And if I do that out real fast, and there I get the tension is about 3,580 newtons. And you better believe that that would make sense, because if you're swinging somebody on a rope in a chair, like this is a person, a human being, swinging them around, that's going to be a lot of force to swing them around. So there's our tension. We've done part A, check. Now I need the speed in the chair. Well, we could do this with centripetal force, because centripetal force is mass times velocity squared over radius. Anytime you're given a circle and asked to find velocity, this is probably where you're going to go, this equation right here. Well, the up and down forces are equal, so we don't have to worry about those for net force. The net force, the centripetal force, would then be the x component of the tension. So T sine 60. So that means that T sine 60, since that's our net force and therefore our centripetal force, equals mass times v squared over r. And we're supposed to find the speed, so multiply by r to get rid of it. Now I've got r t sine 60. I sound like a pirate. R t sine 60 equals m v squared. Divide by m, and I get r t sine 60 over m equals v squared. Take the square root, and we have arrived at v equals the square root of r t sine 60 degrees over the mass. And if I sub those numbers in, v equals the square root of the radius, and notice that the radius is actually not in this picture. Let's draw it really simply down here. So the circle is actually down here in our picture. The string starts here. So this is 15 meters, but we need the actual radius of the circle, so we need this component here. So if this is 60 degrees and the hypotenuse is 15 degrees, we would want the opposite side. So 15 sine 60 degrees would give us our radius. So 15 sine 60 degrees for our radius. So that's because the actual starting of the rope is not at the center of the circle, it's above the center of the circle. So I had to work out what the actual x part toward the center of the circle is. So 15 sine 60 degrees equals the tension, which we found to be 3,580 newtons, times sine 60 degrees, divided by the mass, 179 kilograms. And if I do all that math right there, I get that the velocity is 15 meters per second. Ta-da! The end.